Thank you very much, and thank you very much to the organizer for their invitation. And yeah, I actually had forgotten about the title I sent, because I sent the title a long time ago. So yeah, I think for most of the talk, I'll talk about something else, but then at the end, there will be also this normal form for, so at the end, there will be some, well, not really integrable, but what happens when you perturb something that it's really, really integrable. Okay. So no, the setting is the standard setting of classical mechanics. So we are in R2N with the standard symplectic form, dpj, dqj. And here in this phase, so a way of measuring sets is, of course, volume. So of course, now the maps that we want to consider are symplectomorphisms, so diffeomorphisms which preserve this form. A way to measure set which is invariant with respect to these is volume. A more subtle way to measure sets which is still invariant with respect to symplectomorphism is given by the so-called symplectic capacities. So maybe let me symplectic capacities. So symplectic capacities were introduced in the late 80s by Eklund and Hofer, inspired by Gromov non-squeezing theorem. And let me just introduce them, say, axiomatically. So we have a function on the space of all, on the set of all subsets of R2N with positive values, so non-negative, eventually also, possibly also plus infinity. And this function C, this is our symplectic capacity, should satisfy some natural axioms. It should be monotone with respect to inclusion. Can you see, is it too small? Yeah, good, but you're in second line, so it's not really. So maybe I'll make it a bit bigger. No, they say good, okay. So capacity gets bigger, so less or equal. Then it should be symplectic invariant. Phi is a symplectomorphism. Then phi of A should stay. Then it should rescale as an area. So C of, let's say, R times A is R squared C of A. Okay, to rescale as an area. And the last thing which makes everything really non-trivial is we want to normalize it in such a way that the symplectic capacity of the 2n-dimensional ball is the same as the symplectic capacity of a cylinder. So it's a 2-ball cross R 2n minus 2. And this should be pi. Okay, so this is the 2-ball in one plane, for instance, P1, Q1, and then all the other variables are free. So this is a cylinder. It's an infinite volume cylinder, but it should still have finite capacity pi. Okay, so the mere existence of this capacity is a non-trivial thing. If you have a symplectic capacity from this, you deduce immediately Gromov non-squeezing theorem, saying that you cannot map a big ball symplectically into a thin cylinder by these last properties. Okay, and indeed the construction of symplectic capacity is non-trivial. There are many known symplectic capacities. It's also these axioms do not determine them uniquely, unfortunately. So and in the construction, there's always some non-trivial techniques involved in the construction. But let's say, so if you have Gromov non-squeezing theorem, then from this you get that you have two very simple capacities. One is the inner capacity. It's actually called Gromov width, which is the biggest you look at the biggest ball that you can symplectically embed into your set. So you do sup of pi r squared, such that the ball of radius r symplectically embeds into our set. And there is the outer symplectic capacity. The technical name is actually cylindrical symplectic capacity, which is instead you look at the thinnest cylinder in which you can embed your set. So infimum of, again, pi r squared. And now we want to take this cylinder and A, we want to put it in here, say again, symplectically, okay? And then all capacities are squeezed between these two. Okay, so these are symplectic capacities. And in year 2000, Viterbo proposed an interesting conjecture. So this is Viterbo's conjecture. On so relationship between this sort of two-dimensional measurement and volume. So the conjecture is that if K is a convex body in R2n, then the symplectic capacity of K to the power n should be less or equal than the volume of K. But let's say the volume of K, here I'm measuring with respect to the symplectic form omega 0 to the n. So if you want to look at the Euclidean volume, this would be n factorial, the Euclidean volume. Just using this volume makes a bit constant, a bit nicer. So constant is 1. Okay, and moreover, he also stated that with equality, if and only if the interior of K is symplectomorphic to a ball. Interior of K. In other words, you can think that another way of stating is if you look at convex bodies with a fixed volume, in order to maximize the symplectic capacity, this is maximized by the ball, and of course all its symplectic images, which is what makes the conjecture difficult. So this conjecture is open, but let me just here mention, maybe as motivation, some consequences of this conjecture. So what happens if Viterbo is right? So if Viterbo is right, then one gets a sort of no-squeezing theorem also in the intermediate dimensions. And this is, this is something I investigated, say, 10 years ago with Slava Matveyev. So here is what happens. Now you can look at, so instead of, so now you look at the symplectic projector. So from R to N, you go to R to K. This is really, so I'm seeing R to K as a 2K symplectic subspaces of R to N. And this is just the natural projector there. And then you can look at the such that the image of the ball is still convex. Okay. And then what you get from Viterbo is the following, that if you now take the 2K dimensional volume, say, of the shadow, so you apply your symplectomorphism to the ball, so you get your symplectic ball, which is still convex, and then you look at the shadow of, by projection on the 2K dimensional shadow where you project on this space. This shadow is still big. It's greater or equal than the 2K dimensional volume of the ball in dimension 2K. Okay, this would follow from Viterbo conjecture. So for K equal 1, this is actually true, and this is also true without assumption that the image is convex, and this is again a reformulation of Gromov no-squeezing theorem. For K equal N, okay, it's an equality, this is the identity, but for intermediate case, say for K between 2 and but strictly less than N, if you just allow any symplectic morphism, then you can make the left-hand side arbitrarily small. So the 2K dimensional shadow of a symplectic ball can be really arbitrarily small. There is no rigidity in this case. This is what we showed with Slava. But with convexity, one should still have rigidity. One should still get this optimal inequality. Okay, this is one consequence. Another consequence, actually more striking consequence, was found instead. This is due to Abbondandolo, Karasev, and Yaron-Ostrover. Viterbo conjecture implies the Mahler conjecture. The Mahler conjecture in convex geometry, which states that if I have a convex body, now in Rn, again, a convex body, and it's centrally symmetric. And I looked at the volume of K times the volume of K polar. This is always greater or equal than precise number is 4 to the n divided by n factorial, and which is the corresponding quantity for the cube, and actually it's the corresponding quantity for a family of convex sets known as Hanner polytopes. It's also an open conjecture. Mahler in the 40s, I think, proved it in dimension 2. Recently, Irie and Shibata proved it in dimension 3, but from dimension 4 on, it's open, but it would follow from Viterbo's conjecture. Okay, this just to give some motivation why it can be interesting to study this conjecture. And what is it known about this conjecture? Yeah, as I said, not much. What it's known is that there is an inequality. Where is the conjecture here? Not with the optimal constant 1, but so again, Abbondandolo, Vitaly Milman, and Ostrover. They proved the bound of the form capacity to the n is less or equal than some constant, volume K omega 0 n, where the important thing is that this constant does not depend on the dimension. So if you want this Viterbo conjecture is asymptotically true. Yeah. K is always a convex body in R2n. Sorry, cannot here. This is the polar set. The polar set in the sense of convex geometry. Okay, is the polar of the convex body. Yeah. Yeah. Okay. Yeah, so asymptotically the conjecture is true. So the difficulty in this conjecture is really to get to the optimal constant. And then so the conjecture is true with the optimal constant in a bunch of special class of convex sets. And here there are many results. For instance, again, so I think Yaron has also results in this direction. Then Karasev with Schlenk, but also yeah, well, who did these results on the Hamiltonians of the form kinetic energy plus convex part? Okay, I should have checked. Sorry. Okay, so the conjecture is known in some specific classes. Sharipova. Yeah, and then yeah, Balitinsky has also special confirmation of the Viterbo conjecture for some special sets of the special products, Rn cross Rn, but very special ones. Okay. But here I would like to say something about a recent theorem that I got with Gabriele Benedetti, which essentially says that Viterbo's conjecture is true locally. Okay, and so let me state it correctly. This results say that there exists U. This is a C3 neighborhood of the ball. So by C3 neighborhood means now I'm just considering sets with a smooth boundary, and then yeah, then you understand what it means to be in a C3 neighborhood of the ball. Okay, so there exists a C3 neighborhood of the ball such that whenever a set, which then will also be convex, is in this space, that indeed any, and for every symplectic capacity, C is here any symplectic capacity. Then we have the inequality, Viterbo's bound, capacity to the power n less than volume, with equality, if and only if. Well, in this case, the set is smooth, so we don't have to take the interior. So really, K itself is symplectomorphic. In this case, to the closed ball. So to some closed ball, I have to change possibly the radius, of course. For some radius. Okay, so this is the result. Are there questions on the statement? Is the statement clear? Okay, so in the remaining time, I would like, yeah, well, not really to show you the proof, but say what kind of ideas enter the proof of this statement. So first of all, let me mention, so the novelty here is that we are really in dimension, an arbitrary dimension. In the case of dimension 2, so dimension 4, sorry, so but n equal 2, we had obtained this result with Barney Braham and Umberto Vigniewicz and Pedro Salomao. Actually, we stated for one particular symplectic capacity, but there's some thought we could have also stated for any symplectic capacity. So, but this was only in dimension 4, and the methods were really low dimensional. We were looking at the flow on the boundary, the characteristic flow on the boundary of these sets, and looking at Poincaré sections for this flow. It was a dynamical proof, but really for dimension. And I should also mention that a couple of days ago, still in dimension 2, to improve our result, he actually showed that still in this C3 neighborhood, all symplectic capacities coincide. Okay, and the coincidence of this all symplectic capacity actually implies the Viterbo conjecture, just because the Viterbo conjecture is trivially satisfied by this smaller capacity here, the interior one. Okay, so if you show that all symplectic capacity, say for instance on convex sets, are the same, you have proven also the Viterbo conjecture. Okay, and what Etmar proved is that still dimension 4, all symplectic capacities agree in this C3 neighborhood of the ball. Oh. Now, yeah, arguments in the proof. So the first thing is to go to dynamics, to introduce dynamical systems. And here, the natural thing to do is, so we are in R2N, we have not only the symplectic form, but we have a very good primitive of the symplectic form, say the radial one. I'll call it lambda 0. This 1/2 sum dj dqj minus qj dpj. Okay, this is a primitive omega naught. And then we can, if we assume that 0 is in the interior of our convex body, then, so our convex body will always have a nice smooth boundary. If you assume that 0 is the interior, then the restriction of lambda naught to the boundary of our convex body will define a contact form. I will denote it by alpha k. Alpha k here is the restriction of lambda naught to the boundary. This is a contact form on the boundary. It's a sphere, say, on this 2n-1 dimensional sphere. And where contact forms means just that alpha k wedge d alpha k to the power n-1 is always non-zero. Okay, and then whenever you have a contact form, you have an associated Reeb vector field. I denote it by R alpha k, which is, so it's a Reeb vector field. So it's a way of choosing a representative in the contact, in the characteristic distribution over K. So it's this vector field is defined by, so it's in the kernel of the alpha. So the contraction of this gives me 0, and it's normalized to be 1 over alpha. So the contraction along this vector field of alpha itself is 1. Okay, this is the Reeb vector field, which gives us the dynamics. Very good. And then, so in general, when we have this contact form, say on a closed manifold, we can look at the shortest period of periodic orbits. I call it T-min. This is the minimum over all periods of closed orbits. Alpha. Okay, this is T-min, and the first step in this proof is to observe that if K is C3 close enough to a ball, then T min of its contact form is actually the outer symplectic capacity, so the cylindrical symplectic capacity. Okay, so this is actually not difficult to show. So you start from the ball. The ball. So what is the Reeb vector field in on the ball? So on the boundary of the ball. This is just the vector field which gives us the Hopf vibration. So all the orbits are closed and they all have period pi. Okay, and now you perturb that situation, you will still get some short orbits which will be close to these Hopf fibers. And then what you need to do is to bring, by a symplectomorphism, to bring them into say in a symplectic plane by a symplectomorphism which is so close to the identity so that it preserves convexity. So this is the idea, the proof of this step one. Okay, but once you have this step one, it means that we can now forget about this general capacity and just really work with T min, with this minimal period. Okay, then maybe we also introduce, so in general, when we have a contact form on a manifold, we can define its systolic ratio as T min to the power n divided by volume. So now the setting is we are arbitrary manifold, say dimension 2n-1, with a contact form alpha. Okay, and then we have the systolic ratio is the minimal period to the power n divided by volume. Volume with respect to alpha is of course the volume of M with respect to the volume form alpha wedge d alpha to the power n-1. Yeah. No, just because I'm, well, because I want to, so the Viterbo bound is an upper bound on all capacities. Every capacity is less or equal than this one, but they actually coincide here. Okay, so at least as far as for the bound, then of course we'll have to take care about how to characterize equality, but for the bound, we can work on this. Yeah, thanks. Okay, so this quantity here is called the systolic ratio. The name is borrowed from Riemann and geometry. And our aim is actually to show, no, of course, the contact volume of the sphere by Stokes is nothing else by the symplectic volume of the interior. So our aim here is really to show that the systolic, say locally, rho is maximized, say locally, by the contact form of the ball, by the standard contact form on the sphere, which is the one which I'm denoting by this. Okay, this amounts to this. And a theorem that we proved is exactly saying this in a more general setting. So what is special about the ball? And what is special about its boundary, the sphere? What is special here is that the Reeb vector field has, so the Reeb flow is periodic and all its orbits have the same minimal period. So, and let's aim to this contact form with this property. So let's say that a contact form alpha, contact form on M is said to be Zoll if the flow, the red flow, also the flow of R alpha periodic with all orbits of the same minimal period. So in other words, it's you have really a free S1 action. It defines a free S1 action. Okay, again, the name Zoll is borrowed from Riemann geometry. Zoll metrics are metrics whose geodesics have this property. They're all closed, all same length. Okay, so these are Zoll, and the theorem that we proved is that these Zoll contact forms are local maximizers of the systolic ratio. Hood. So if so, alpha naught is Zoll, say on a manifold, on a closed manifold M, then there exists a C3 neighborhood of alpha naught in the space of one form, such that, let's call it again U, such that the systolic ratio of alpha is less or equal than the systolic ratio of alpha naught for other alpha. Okay, and with the quality in this case, if and only if, here we could say if and only if alpha is Zoll, but actually we can also say more, if and only if, in this case, alpha is really conjugated to alpha naught. So up to a diffeo, so there exists a diffeo such that phi star alpha is, say, a multiple, a constant times alpha naught. Okay, so yeah, Zoll contact forms are local maximizers of the systolic ratio. And this actually answers yeah, a question which was opened some years ago. So the idea of defining the systolic ratio and embedding actually problems from Riemann geometry into studying them with techniques from contact geometry is actually due to Alberto Abbondandolo and Balachev. So yeah, some years ago, they proved the converse of this theorem, namely they proved that if a contact form is a local maximizer of the systolic ratio, then it has to be Zoll. Okay, and then they had some results in the direction of this, and this in some sense, yeah, answers their question. So it's true that at least in the C3 topology, Zoll contact forms are the local maximizers of the systolic ratio. And I should also mention that it's really essential that you are close. If you go far, again with Braham, Rignetz, and Salomao, we showed that the systolic ratio can be arbitrarily large. Okay, this we showed. So yeah, on every contact manifold, you can find contact forms with arbitrary large systolic ratio. We showed this in dimension 3, and then Murat Saglam generalized this to any dimension. Okay, so this is the theorem we are now aiming at. Maybe just what is missing. So once one has this theorem, then you get, as I explained, the the local version of Viterbo, but then we still need to discuss the equality case. Okay, so what happens now if I have a convex set which is close to the ball and satisfies exactly the equality in Viterbo? Then we will get its flow by this theorem on the boundary will be Zoll. Okay, and so the extra thing that we had to prove, this is true, let's state it as a proposition, is that now we are back in R2n, and if K is, say, C3 close to the ball, and alpha K is Zoll, the standard contact forms on the boundary is Zoll, then K itself is symplectomorphic to a ball. Symplectomorphic to a ball. Right? This is also true. The proof here uses generating functions to construct so generating functions and yeah, Moser's argument to play with contact forms. Okay, then now let's focus on the theorem local maximality of Zoll contact forms. Are there questions? Yeah. So in general, locally yes, In generally, Zoll contact forms are classified because you have the induce. So it's a free S1 action, and then you look at the quotient, and yeah, what we get is this Booth-Bewang form. They're all, so the quotient will be a symplectic manifold. So it's an S1 bundle over a symplectic manifold. And but then globally, say if you give me any contact manifold M, then yeah, I don't know how, if there is only one Zoll one, or if there can be more. So globally it becomes a difficult question, but in some sense it becomes a question now in, yeah, if you want in algebraic topology to understand this, and probably something is known. Yeah. Yeah. Yes. So in general, I don't. So Weinstein conjectured that this kind of flows on any closed manifold do have periodic orbit. So if you believe in, and this Weinstein conjecture has been confirmed in many cases. So, but strictly speaking, when I define, yes, when I define T-min, since the Weinstein conjecture in full generality is not proven, I should say here T-min is plus infinity if there are no periodic orbits. But in our case, everything is perturbative, and actually the existence of these closed orbits will actually follow from the theorem that I'm about to state. Yeah, but in general, yeah, this T-min might be even plus infinity if the Weinstein conjecture is wrong. No, unfortunately not. They are you can make them C0 closed, but there is still a gap. It's still not, so if this C3 is, so I don't think this C3 to be optimal. This C3, we have now different approaches to this result, and this two-dimensional, and the one I'm showing, I'm going to show. And every time, so we need the three derivatives, but for completely different reasons. So, and also if you think of the origin, because actually I didn't say it, this theorem, of course, has also then applications to Riemannian geometry, because then you can say something about what happens when you perturb Zoll metrics on a. And also there you would like to say you want to perturb a metric C2, because that's a regional way to perturbing that, yeah, this unfortunately we don't have. So, but if I were to bet, I would say it should still be true in C2, but C1 probably not. But with the only evidence is, you know, try to prove these things, and this is what, no more than that. Okay. Okay, so how to address now this local systolic? So this actually is a consequence then of a third theorem we also proved with Gabriele, which is finally a normal form. So the normal form is assume that we start with alpha naught. So alpha naught, that form. On M. And then we perturb it. How can we put the perturbation in some special normal form? This is what we'll say. So the theorem says that, so there exists, actually here it's enough to have a C2 neighborhood. U of alpha naught, such that whenever alpha is in this U, there exists a diffel of M. This diff, of course, will be close to the identity, such that the pullback of alpha with respect to this diffeo has the following form. So it's a function S times alpha naught. Then there is one form eta, and then there is a differential df, where I have to tell you what all these guys are. So S is a function, but it's a function which is invariant under the S1 action defined by alpha naught. So S is in, say, omega 0 M, but it's phi alpha 0. So this is the flow of defined alpha naught invariant. F is also a function, and it has zero average on this big, with zero average on the orbits of phi alpha naught. Eta instead is a one form. Which vanishes along the direction of the Reeb vector field of alpha naught. Okay, I just tell you this, this is nothing, this is always true. So if I take, say, any one form, I can always say, I define S just to be the integral of this, I average, I define S, the function is just the integral of my new form here, and then what remains show that it has. So this is nothing, but what's relevant is what comes next. Yes? This is the flow of the unperturbed flow, is the fully periodic flow, the flow of the Reeb vector field of alpha naught. Yes, the S1 free S1. Ah, just dt. Just here time is given by by my reference flow. Yes. Okay, so what comes next is, so what comes next basically means that these new things are not really independent, but they are both related, somehow linearly related with S. Okay, and so here is the thing. If I now would do, I contract my d eta on the Reeb vector field, what I get is some f. Here f is a linear endomorphism of the cotangent bundle, lifting the identity. Okay, so in particular, when ds vanishes, also this vanishes. That will be important. And then there is a similar thing which is less now relevant about this, but this is not so relevant. So let me just say you use this theorem without writing anything to prove the local systolic thing. The thing is now that this S, because of this last property, this function S becomes sort of a finite dimensional variational principle to detect periodic orbits. This S is an invariant function on the total space M, but it's invariant with respect to this S1 action, so it descends to a function on the quotient. And if you look at critical points of this function, the lift of critical point of this function, because of this last thing, will be true periodic orbit of my new perturbed things. So it means that if I want to find periodic orbit, I just need of alpha, not alpha naught, of alpha. I just need to find periodic orbits, critical points of S. And then the next thing that you have to do is to express volume in terms of this S and start playing with that. So the crucial thing is this normal form. And just to add a reference, so as far as I know, this normal form is new, but method of proofs that we have follow some literature. So in the 70s, so in particular, Moser and Weinstein studied this sort of normal form, but not for forms, for vector fields. And the one which is closer to what we do is a paper from 1980 from Botkol, who was a student of Einstein, who studied exactly what happens when you perturb a vector field, whose flow is defining a free S1 action. And this is the kind of techniques that we use in proving this theorem. Okay, thank you very much for your attention.
Questions, please.
About the? Mm-hmm. Yeah. So it's a sort of a it's a complicated construction. It's not an easy thing. It uses some constructions that were introduced by Larry Guth when he showed that the non-existence of capacities. If you know this thing of Larry Guth, then so there is a first step where you embed a ball. So first step, your ball, you put it into a very long ellipsoid, but then this very long ellipsoid, you see it in 2 torus cross R2n minus 1. And then the thing, this was a construction by Polterovich. And then by this, you have to show that by a Hamiltonian perturbation, you can remove a point. And it's a very ad hoc construction, and these things. in principle, it should be possible. So this function S, well, this function S should see the low part, because it sees only these periodic orbits bifurcating from this. So I would expect that there is a homomorphism between the Morse complex of this to the complex, but as far as I know, yeah, we didn't work out the details, and as far as I know, nobody did. But yeah, there should be something. Yeah.
You already mentioned the consequences of Riemannian geometry. So you actually look at
yeah. So now an interesting question. Yeah, in Riemannian geometry is not Tolic inequalities. When can you bound the length of the shortest geodesic by volume? Okay, and which is a problem which is well studied and with many results in the non-contractible case, but you can ask it also, for instance, on the two-sphere. So, for instance, on the two-sphere, this kind of result will tell you that, yeah, if you perturb just a bit, on the two-sphere, the thing is that there are many Zoll metric, not just around one. There's a whole infinite dimensional family of Zoll metric. And so this result will say that, yeah, they're all local maximizers of, in this case, of the Riemannian systolic ratio, where length of shortest closed geodesic divided by Riemannian volume. But this is now true for all, so there are many examples of Zoll geodesic flows, symmetric spaces, and this is now true in every dimension. But it's a local result.
So, as a motivation, you mentioned Mahler conjecture, and the conjecture optimal convex body for a conjecture is understood by the cube, right?
Not only the cube.
Not only the cube, but there is also some other.
Yeah.
And the canonical solid contact structure is on the standard sphere. Yeah. Are they related?
Yes. This is actually was solved by Yaron. So when you do Mahler, you actually work at cube. So you work always at K cross K polar. Yeah. What happens is that the cube cross the polar of the cube, the interior is symplectomorphic to a ball. Yeah. Okay, so I don't know if this is proven yet, but so the conjectural set of minimizers in this case for Mahler is this Hanner polytopes. This Hanner polytopes is whatever. So you start from a symmetric interval, and then you are allowed just to do two operations: take polars and take products. Then you start, you have an interval. Of course, the polar here doesn't make any sense. So it's still an interval. So you make a product and you get a square. Yeah, the polar is still a square, but now you take, when you go to dimension 3, now, so you have the cube, and now you have then the polar is the octaedron. And this is a new Hanner polytope. And I think conjecturally, Hanner polytope cross its polar. The interior should be symplectomorphic to a ball. And I remember that Felix Schlenk and Karasev had an argument for that, but I don't know if it's finished yet, that project.
The result you mentioned, I mean, the previous slide, that solid contact structure are somehow optimal for systems.
Yeah.
Can they construct other local minimizers for Mahler conjecture, but this polytopes?
So as far as I know, for Mahler, it's proven that all these Hanner are local minimizers. This is, but local in a much weaker topology in our case, so it's a better result. They have local, really Hausdorff in the Hausdorff distance, but as far as I know, there are no other local local minimizer for Mahler. So those are again. So Zoll things are local minimizers. Yes.
In one conjecture, there is no other known but
I see what you mean. No. The thing is, here you have much more freedom to play with stuff. But what you can do is you can, instead of looking Zoll for flows, you can do the next step. Say that you have a free an S1 action, but it's not free. This would be called Besse. And there one has, again, some optimality, some systolic optimality in this case. Yeah.
There are no other questions. Now, we resume as 5:30.